When an executive types a simple prompt into an AI tool, a single idea explodes into perfectly structured, functional software in seconds. For leadership, the takeaway is straightforward. If a machine writes code this fast, development timelines can be compressed, and engineering teams can operate with a much leaner headcount. This expansion happens flawlessly in a greenfield environment, an unobstructed workspace where AI operates without historical constraints. But real enterprise value exists in brownfield systems. These are massive, tangled webs of legacy code, patched together over a decade, full of specific quirks. Executive dashboards may report a 400% increase in code generation during a sprint, but those metrics ignore the friction created when that code enters a complex legacy architecture. Prioritizing raw AI speed inside these environments layers on invisible, systemic risk. In the engineering trenches, the fundamental nature of the work has shifted. Developers are spending less time typing code and more time endlessly reading it. Traditionally, writing logic organically builds a mental map. Each block illuminates, establishing an unbroken chain. In the AI reality, hundreds of generated lines are abruptly dropped in. These remain unlit, leaving massive context gaps for human integration. This defines cognitive load, the mental bandwidth required to parse, verify, and integrate this rapid, context-blind AI output. Without specific business context, AI tools frequently hallucinate variables or rely on deprecated libraries, presenting these errors with absolute confidence. Senior developers are now functioning as senior editors. They are proofreading highly technical manuscripts every single day, assuming full responsibility for code they didn't actually write. Squeezing a shrinking team to verify a 400% increase in output pushes human cognitive bandwidth to its breaking point. A high-stakes deployment reveals the danger. An AI-generated update for regional tax codes is pushed to the edge of production under a compressed deadline. The automated testing layer, also generated by AI, returns a pass rating, signaling that the update is safe to ship. Below sits a context-blind error. This logic tree shows data passing through a new node, triggering a red corruption cascade. The error bypass tests because the outer syntax shell is intact, while internal routing paths are misaligned with business logic. Catching this requires a manual, exhaustive trace of the database calls. Tracing these convincing AI mistakes can be more mentally taxing than writing the original logic from scratch. A delayed feature makes investors anxious, but deploying a catastrophic billing failure will completely destroy the company's reputation. Responding to a near miss of this scale requires a structural overhaul of how human capital interacts with generative tools. This transition sets a new operational standard for how engineering teams are structured in the age of generative AI. In this model, the developer's role officially transitions from code writer to code architect and auditor. Leadership must also reverse the trend of shrinking teams and instead reinvest heavily in quality assurance support. This shift upgrades the QA function. On one side is the high-volume data funnel of AI generation. On the other is a rigorous, multi-layered filtration matrix where specialized AI output verifiers provide manual approval. This framework repurposes the speed of generative AI to fund the time needed for rigorous, human-led quality assurance. Reliable enterprise velocity is the product of balancing high-speed generation with absolute human-verified stability.